just don't go. Okay. So my name is Zheng Wang. So in PLDI this year, we have a 1-minute pitch session. The idea is that each PLDI speaker will spend 1 minute to convince you to come to their talks. And today we have 24 excellent papers. So we're going to start from the first one.
Just before we start, so the break is opening now, especially for the Korean folks, because right after the pitches, we'll go on with the Korean sessions. So if you want to have coffee, you have to try to schedule dynamically. And also after the pitches, we'll go directly for PLDI to the parallel sessions on Aula Master and civil engineering. Thank you.
Hey, so first talk of the first session, demo match, API discovery tool. So the big question is, how do you help somebody discover functionality in a complicated API when they can't even name what they want? So the demo match solution is you let them do a demonstration of the desired functionality on some other application that uses the same framework. And so what we're able to do is take that demonstration, match it against the database of program behaviors, and from that, give you a code snippet that tell you how to use the functionality. If you want to know how it works, come to the talk.
Hi, everyone. So I'll be talking about similarity of binary procedures. Why you should come? Well, if you're a developer who's interested in what's happening when you reuse code in the binary, or if you're a security researcher who looks for possibly vulnerable procedures in stripped binaries and you need help doing that, then we'll talk about how we find similarity. We use some crazy ideas like reapplying optimizers on lifted binary code. And we also use statistical reasoning to find what is the important part of the procedure which avoids false positives. So we have some nice accurate results with scaling over millions of binaries. So come check it out. Thank you.
Hi everyone, I'm Osbert, and today I'll be talking about synthesizing program input grammars. So if you've ever had a program that takes structured inputs such as XML, and you want to do something like grammar-based fuzzing, or create a whitelist of valid program inputs to improve security, or reverse engineer the program's functionality, but then you realize that you don't have the program input grammar, so you can't do any of these things, well then I'm going to tell you about an algorithm that'll solve all your problems. So this algorithm just needs access to an input example and also black box access to the program, and then it'll use active learning to learn grammar that approximates the program input grammar. And if you want to know how this works, come to my talk. Thank you.
Right, so this talk is about making machine learning easier by applying programming language technology. So the main problem is that probabilistic inference is analytically intractable in general. And consequently, this means in practice, we have to design and implement approximate inference algorithms. And notably, these algorithms can often take a really long time to run. So come to my talk if you want to figure out how to build a compiler for a probabilistic programming language. Thanks.
Cool. So my talk talks about how to optimize the cache locality of a recursive program. So oftentimes you may have a divide and conquer program, maybe a stencil that's written in a recursive way. A lot of fork join programs are like this, and you want to improve the locality by performing a very powerful analysis like time tiling. So traditionally, polyhedral compilers would be used, which require the code to be very analyzable and affine. And for recursive programs, it's a lot harder. You need IPA analysis. So in this paper, we look at a new approach that actually does this fully dynamically at runtime. So we have the user specify data effects and then use that to dynamically interleave recursive programs to accrue significant locality benefits. And we find this is competitive with other strategies.
So pipelines of comprehensions over streams of data are common in data analysis workloads. And these can include functional comprehensions that don't have any states and effectful comprehensions that incorporate some loop carriage state. So we want to allow modular development of these pipelines that can include both functional and effectful components. And then we want to fuse them into a single representation from which we can generate efficient code. We compile our front-end languages into branching symbolic transducers, and the fusion procedure we have developed for these uses an SMT solver for pruning, and it also exposes some additional opportunities for further reductions we have developed. After fusion, we generate efficient code, and the evaluations have shown large speedups over handwritten and traditionally fused code on a variety of benchmarks. So I hope to see you at my talk to get all the details on how we achieve these speedups.
So my work is about how to generalize strength reduction with triangular inequality. And one key to my work is about how to make faster comparison without changing the final result. For example, if you want to know like which country is further away from Spain, Germany, or Greece, one way to get it is to one way to answer it is to get the exact distance and do the comparison. But in this case, we can say rough bounds are already enough to draw the right conclusion. And our work is about how to automatically replace those expensive distance and vector products computations with bounds in data analytics. And our results shows that we could achieve magnitudes of speedups for those machine learning and data mining algorithms. So if you are interested about how we achieve this huge speedup, please come to my talk. Thank you.
So you've written a peephole optimization because you want your code to go faster, and you found a common pattern that shows up a lot that could be written better. But you tried it out, and it works for all your test cases, but you weren't able to prove that it was correct because there's some other cases where it was wrong. So you need a precondition that'll indicate when the optimization can be applied. And that can be real hard to do, real annoying. You need to specify when it's valid, but you don't want it to be too strong, and you don't want it to be too complicated. And so our tool can help with that. It infers a precondition automatically for a peephole optimization that's specified in the Alive language. And it will find the predicates that it needs in order to write your precondition. And it will make sure that your precondition doesn't try to divide by 0 and crash the compiler. If you're interested, see me at the talk.
Yeah, hi, I'm Andreas Rosberg, and I'm going to talk about WebAssembly. So WebAssembly is a new portable code format, the purpose of which is to A, bring near-native code performance to the web, and B, also to break the monopoly of JavaScript as the only executable code format on the web. And this might be remarkable for two reasons. First of all, it's the first time I think some technology like this was developed in collaboration between all the major browser vendors, so it's coming to all of them almost simultaneously. And also, as far as we know, it's the first industrial strength language that was published and defined along with a complete formal specification. And I'm going to talk about that a little bit. So, and finally, you're probably going to stumble over this technology in the future, maybe even outside the web context. So if you come to my talk now, you may be among the ones who say, I was among the first ones to be able to rant about it. Okay, thank you.
Hello, everybody. So when writing compilers, there's a common conflict between writing a modular compiler and writing a fast compiler. In my talk, I'll introduce a new method that we've used to build Dota compiler, the future Scala 3 compiler, to write the compiler which is easy to maintain while also being fast. The methodic allows to speed up the resulting compiler by 35% and reduce the GC promotion rate by 50%. The talk will also include a very interesting evaluation of performance and very interesting artifacts, which, to the best of my knowledge, have never been shown for Scala compilers in particular and compilers in general. So please come if you're interested in low-level performance too. Thank you.
Hello, everyone. We have built a new programming language for energy-aware programming that encourages programmers to take an active role in the energy management of their software. And, that programming language is called ENT, and we have a proactive side that programmers will use to annotate program components with expected energy behavior, and then we regulate that, what we believe are consistent communications across those program components. We also have an adaptive side that allows certain decisions to be delayed until runtime. And the centerpiece to this is a type system that combines both static and dynamic typing. And if you're interested, please come to our talk.
Hello everyone, I'm Kapil Vaswani, and my talk in the afternoon today is about the very high cost that we all pay by using garbage collection to get memory safety in highly performance critical systems. And this is a cost that's going to increase as we build applications that consume several hundreds of gigabytes of memory. In the spirit of Brexit, I claim that we need a GC exit. So I claim that we need to leave the garbage collector behind and instead take back control over memory management. And we propose to do that by adding a very simple delete primitive to starting with a safe language, adding a delete primitive and a dangling reference exception. And I'll show you that if we do these, then we can get back high performance and safety without compromising on the simplicity of the programming language. And if you are still not convinced about GC exit, then come attend my talk. Thank you.
Hi. So just like CPU programs, GPU programs have data races. And the way to find the data races in a precise way is using a vector clock-based algorithm. But vector clocks don't scale that well on GPU programs that have hundreds of thousands or even millions of threads. So to find out how to build an algorithm for race detection on GPU is precise based on vector clocks, but scales well to those counts of threads while supporting the entire memory hierarchy of GPUs and the different locking and synchronization mechanisms of GPUs, come to our talk today. Thank you.
Hi, I'm Steve Friend from Williams College. For the last number of years, my colleagues and I have been working on improving the performance of precise dynamic race detection. We've designed a number of analyses to do this, including fast track, red card, and slim state. The key starting point for this work was identifying redundancy in earlier analyses like DGIT that could be eliminated without compromising strong precision guarantees for the analysis. Despite our work, these analyses can still have fairly high overhead. This afternoon I'll be presenting a new analysis called BigFoot, which eliminates over 50% of the overhead from our earlier approaches. The insight behind BigFoot is that we can use a fairly sophisticated static analysis to optimize exactly where and how a dynamic analysis will check for races in the target program. We're really excited about this work, and I look forward to telling you more about it this afternoon.
Hello all. Traditional sound race detection techniques based on happens before relation are known to miss a lot of races. Other techniques that try to overcome this shortcoming often tend to not scale because they're not linear time as happens before race, and they have to resort to what is called windowing. That is not desirable because that can also miss happens before races. Our contribution is this new partial order called weak, cost of precedence. It is probably more general than happens before or CP. Further, it's sound. It doesn't raise any false alarms. The most important part being that it has a linear time vector clock algorithm, and that is the source of all the efficiency. We show that our algorithm is optimal in terms of space and time, and further, our experiments are promising. We show that we can handle really huge traces and still have running times comparable to happens before. So for more details, please come to my talk at 2:50. Thank you.
Hi, my name is Marina Billis, and our topic is systematic black box analysis of collaborative web applications. So we are looking at distributed web applications where there are several clients, where web browsers run, and different users make concurrent changes to a shared document in a collaborative editor, which are then synchronized via notion of eventual consistency. We want to find concurrency bugs in these kinds of applications, and the challenges for finding concurrency bugs are the huge state space that needs to be explored and the overall complex and distributed nature of the application. We present our approach and we show some results of some bugs we found, for example, in Google Docs. Thank you.
Hello everyone. So this work is about to achieve high coverage for testing floating point programs. So Our goal here is to generate a test input to cover programs with those complicated constructors such as floating point arithmetics or some complicated nonlinear properties, or even with some unknown external functions. So what we have is a magic transformation of converting the testing problem to a mathematical optimization problem. And our result is actually very promising. So our tool can achieve about 90% branches in this sound math library in only 7 seconds. And compared with the well-known AFL fuzzer, we can achieve 80% more branches. And for the runtime, we can improve the runtime by almost 10 times. And compared with UCL's Austin testing tool, we can achieve 40% more branch coverages and bring about several orders, 3 orders of speed ups. So if you would like to know more about this magical transformation, please join me in the afternoon. Thank you very much.
Hi everyone, I'm Buddhika and I'm going to talk about instruction funning. Quite a funny name. So what do profilers, debuggers, and compilers have in common? So they all use program instrumentation. So with instrumentation, we can gather statistics or even dynamically optimize running applications. But we need to limit the overhead of instrumentation in order to keep the, minimize the observer effect. And also when debugging, we need to be able to attach probes anywhere in the application. But current techniques incur a huge overhead when you attach probes to the application and when running them. So we propose this new technique called instruction funning, which can instrument at any instruction of the application. And more importantly, our technique is several thousand times cheaper than the current state of the art. So if you're interested in this, come see at my talk. Thanks.
Hello, I'm Emmanuel Dantras. So ARMv8 comes with 2 instruction sets, the new 64-bit instruction set and the old 32-bit instruction set. Now, supporting 32-bit instruction set has several costs in power, area, performance, and processor development time. So what if we got rid of it? The problem is nobody's going to buy your chip if you can't run all the legacy applications. So one solution would be to just translate all this legacy 32-bit code into 64-bit code and software using binary translation. But binary translation is known to have runtime overheads. Well, does it really? We disagree. So we created MemberX64, a dynamic binary translator which has such low overhead that on the same processor with the same 32-bit binary, we can run SpecCP 2006 faster under the translator than it would run natively. If you want to see how we do this, come see our talk at 5.
Hello, I'm here again to present another work on compiler testing. So in this work, we consider the program enumeration problem for compiler testing. So the problem is that give you a program, how do you enumerate all these program's variants? The key insight of this enumeration is that by enumerating the programs, it is possible to exploit all the variable usage patterns. By exploring that, it is possible to trigger multiple compiler optimization passes and to find bugs. And the technical challenge for our problem is that how to efficiently enumerate the program. And our algorithm achieves about 6 orders of size reduction. So our result is, again, very appealing. And in half a year, we are able to find about 200 bugs in 2 mainstream C compilers. And we are able to find crashing bugs in Concert front end and also 2 research Skeletal compilers. And see you in the afternoon. Thank you.
Compositional recurrence analysis is a static analysis that infers numerical loop invariance by computing recurrence relations that are implied by a loop body and then computing their closed forms. The question is, how do we apply composition recurrence analysis in an interprocedural setting? Or more generally, suppose that we have some method for approximating the transitive closure of loops. How do we apply that to compute summaries of recursive procedures? At first glance, this seems to be impossible because the set of paths of a recursive program correspond to a context-free grammar, and the tools that we have for analyzing these paths essentially corresponds to regular operations, right? We have something like a Kleene star operation. So this afternoon, I'll explain one method that makes this possible and also practical. So it's implemented in an abstract interpreter that has comparable precision to software model checkers, but is much faster.
Hi, my talk is about context-sensitive pointer analysis. In a context string-based approach to pointer analysis, data flow facts are tagged with strings that are described how the method is invoked. The problem with this approach is that local data flow facts, or facts that are invariant with respect to a method's caller, is enumerated redundantly. Borrowing ideas from the context-free language reachability-based formulation of pointer analysis, I present a unifying abstraction called context transformations that is more efficient. In addition to the efficiency evaluations, I'll present the precision differences. If you're interested, come to my talk. Thanks.
Good morning, everyone. I am Tian Tan. This afternoon, I will present our paper, Efficient and Precise Pointer Analysis, Modeling the Heap by Merging Equivalent Automata, at Study Analysis Session 5 p.m. In this paper, we propose Mahjong, a new heap abstraction for pointer analysis. We target type-dependent clients such as co-graph construction. Our goal is to improve the efficiency of pointer analysis while preserving the precision for these clients. We propose type-consistent objects, and our key idea is to merge these objects by checking the equivalence of sequential automata. Our results are promising. For 3-object sensitivity, the most precise analysis we use, we can achieve a speedup of 131 times while causing the precision loss of only 0.1%. And for the all analysis we use, we can achieve a speedup of 15.4 times while the precision loss is only 800%. If you want to know more details, please come to my talk. Thank you.
Hi, I'm Anirudh. I'll be telling you about deadlock detection for asynchronous C# programs. You've probably heard of async await. It's either in your favorite language or coming there soon. If you've always wondered what the hell this is about, you should come to this talk. And developers are heeding the call of precedents everywhere to create more jobs. So they've very kindly used this feature to create deadlocks in their programs, to create jobs for us in the program analysis community. So we'll tell you about this new program representation that we have devised to catch these deadlocks, and hopefully you'll be able to use it in your analysis of asynchronous programs too. And finally, we'll tell you a little bit about our tool that found 43 deadlocks in C# libraries that developers care about. They fixed 40. So clearly, mine is the last talk of the day, so please justify your funding agencies and be there.
So thank you. Now we have the coffee break outside, and the next parallel session starts at 10:50.
Thank you, John. So please take a moment to recharge after the great keynote and all this madness. I think that was exciting. So we are starting at 10:50 sharp, and it takes 5 minutes to get there. So recharge, but be aware of the time.